Welcome to Dr. Jed's continuing calculus video series. Today's lesson is part of section 5.2 from Rogowski, the part that's computational. So we're going to learn about the general form for rectangular approximations. This involves a partition P, and we'll learn what this means. This is the norm of P, and it's important for finding limits, and then we'll do some examples. So that's what we're going to do today. So, first off, here are some rectangular approximations for area that we learned. The left point sum, the right point sum, the midpoint sum. We also learned about the trapezoid sum, but today not so much. We're not going to do that. We're really concentrating on these. And in the last section we learned that the limit as n goes to infinity is the true area. It makes sense. If you take rectangles and you make them thin enough, you're going to basically catch all of the area you want. But those aren't really the only ones we could do. We could do one where it's bigger. We could do one where it's smaller always in the function. We could do one where it's 3/4 of the way to the end of the point, somewhere where it's like a radical number, like a multiple of pi in there. There's a whole bunch of ways to do it. So how do you write all this out? To generalize it, we have rectangle approximation. That's a rectangular approximation of the function f with a partition P and a representation points, representative point C. What we're going to do is we're going to break up the rectangles, the region that we're going from x equals a to x equals b. We're going to break it into pieces, into partition. And in each partition, we're going to take one point C. So here, down here is an example of the function. The function goes like this and comes back up. And we break it into a partition, starts at A, ends at B, and we're going to break it at x1 and x2. So there's only 4 points in the partition. This one, this one, this one, and that one. So notice the partition is 4 points in a row. The first is always the start of your interval. The last is always the end of your interval. And for each of those regions, we use a point to find the height. So for this first one, we choose x1 to determine the height. We're using f of x1. The next one, right there, the height is determined at c1. We use f of c1. And the next one, over here, we're using the height at this particular point. We just pick that point, go up, and that determines the height. So our representative points are x1, c1, and c2. This may look a little funny, but it's actually really easy to use. So let's take an example of this. Well, first of all, before we do an example of it, there's another piece we have to worry about, the norm of P. It's the widest partition piece. So over here and here, the widest one, clearly, look back here, narrow, kind of wide, really wide. This is the widest one. So the norm of P is equal to the width of that, which is B minus x2. So what do we get? Well, the theorem says when this limit exists, it's equal to the area under the curve. I put under in quotes because, as you notice, sometimes we go below the x-axis. So under is kind of a vague sense. It's the area approximating the function from x equals a to x equals b. And how does this limit work? This is a different kind of limit than we normally use. It's not n going to infinity, or n going to 0, or x go to 0. It's the widths going to 0. We're saying, however you do it, make the widths, as the widths kind of get smaller and smaller and smaller and smaller, those rectangles should get closer and closer to the true area. Notationally, this is a little bit awkward. So we use down here. The area is this. The integral from a to b of f of x dx. So what does that mean? That means, well actually, first off, you should notice this is similar to something we've seen before in section 4.9. But it's a different thing because it's got a number here and a number here. This dx is not optional, it's part of it. But how do you figure that all out? How do you do this? Let's do an example. You'll find it's a lot easier than it looks. So here's an example. The function is xe to the x, which grows very fast. I'm going from x equals 0 to x equals 3. And if you notice, 0 is right here, 3 is right there. So there's the function. We want the area under this curve. Excuse me. I chose a partition already, just at whim. 0, then 1.4, 2.6, and 3. So 0 is right here, 1.4 is right there. Notice that's the first rectangle. 2.6, there's the second rectangle, and then 3. This may not be drawn to scale. Some of these are wider and narrower. So actually, how do you figure out how wide they are? They're no longer all the same width. So how do you figure the widths? Well, from here to here, the width is 1.4, because it's 1.4 minus 0. How about from here to here? The width, if you're going from 1.4 up to 2.6, the width is the difference. It's 1.2. And the last one, from here to here, the width is 0.4. So those are the widths. I'm choosing representative points. They have to be in those intervals, or else it doesn't really make sense. But from 0 to 1.4, the one I want to do is 1. Why? Because it's a nice function point. From 1.4 to 2.6, I'm choosing 2.0, because that's also a nice point. And then from 2.6 to 3, I don't know, I couldn't think of a nice point, so I chose 2.9. Now, when you do this, you want to do it so that you get good points, but the rule here is we're just calculating it out. We're not worrying so much about all of this. So what is this? This RFPC, excuse me, it's the width times f of the first representative point, remember that's over here, plus 1.2, that's the second width, and the representative point from there is 2.0, and 0.4 is the third width, times the representative f of the representative point, not the representative point, but plugging it into the function up here. So, what is 2.9 e to the 2.9? Well, you've got a calculator. I don't, but I already did it. That's what 2.9 e to the 2.9 is. That's what f of 2.9 is. So here's the numbers. I wrote them out so I could figure them out as I go. 1.4 times that, 1.2 times that, and so on. You get this, you get here. This is our FPC for that particular P and C. Notice, the norm of P, the widest of these, is 1.4. Why? Because that's the biggest of those. So what would this turn out to be if the norm of P went to 0? Well, if I make these all, lots and lots and lots of rectangles, no matter which point I picked in there, the amount of error, the amount I'm missing or the amount I'm over, would go to almost nothing. And we'd get the true area. That's what the theorem says. But for now, all I want to do is be able to calculate that. So let's do one more example. I've left it kind of open. It's a simple function, f of x equals x squared. We're going from x equals 1 to 2. So the idea here is, well, let's experiment. Here's what the function looks like. From here to here. And I don't want to take a lot of time here to calculate, but we could pick, say, 1.5 as the middle. That's what we would do in the left-hand rules, or the right-hand rules, or the midpoint rules. We don't have to here. We could do whatever partition points in the middle we want. But let's do that. Why not? So our partitions can be 1.0, 1.5, and 2.0. I need to pick some points in between there. This is hard to really see as 1.5. So in between 1 and 1.5, I need some representative point. I'm going to pick 1.1 because it makes me happy. So 1.1 is right about there. And I need a representative point on the other side. How about between 1.5 and 2? How about, I don't know, how about 1.6? And that's right about here. So how does this determine what we're doing? Well, that determines the height. The C points determine the height of the function. Each rectangle is going to be that tall. So those are the two rectangles we want. So R of FPC, well, we need the widths. What's the width of this? How far did we move? It's easy. Do that minus that, you get 0.5. How far here? It's also 0.5. There's no reason it has to be the same, but truthfully, there's no reason it can't either. So what do we get? We get 0.5. That's the width for the first one, times f of the first point, plus the width of the second one, times f of the second point. Notice, by the way, how many points in our partition? We have 3 right here. The starting one, and the middle ones, and the end. How many representative points? Well, 1 for each interval here, so 1 fewer points in here than here. However many points do you have in P, you're going to have 1 less in C. How do you do this? Well, first of all, what is the norm of P? It's the smaller of these two, or the smallest one we have. And since they're the same, that's easy. This is a narrower partition than the last one, because there's nothing particularly wide. That doesn't guarantee it's more accurate, but in general, the narrower your biggest partition point is, or partition width is, the better your approximation. So let's finish this off. 0.5 times the function 1.1 squared. So it's 1.1 squared is 1.21 plus 0.5, 1.6 squared. So we get 0.605 plus 1.28 is 1.885. Now, is that the right answer? Is that the best approximation? Well, truthfully, if you look at the calculation, I chose points that were kind of early in the interval. So there's a little bit of over right here and a lot of under. A little bit of over, a lot of under. This is probably too small. The real answer of the true area is a little over 2, actually. So we are definitely under. But, and actually, how did I do that? How do I know the true area is? That waits till the next section. Not the next part of this section, but the next section, 5.3. But hopefully this gives you an idea how to calculate out these RFPCs, which is what we're going to be doing today. Until next time, this is Dr. J.